I've gotten a lot of questions recently about the hardness of MagnaCut in various knives that have been announced. Some are implying that MagnaCut heat treated to certain hardness values are suboptimal or even bad. So I wanted to talk about what hardness means and doesn't mean, why knife manufacturers go for certain hardness levels, and why they don't choose something else. Sometimes the reasons are good and sometimes they aren't. Some reasons are practical based on limitations in heat treating and manufacturing, though sometimes they have the customer in mind when making their decisions. So I'm going to explain some of those limitations and specific times when heat treating decisions can lead to bad performance, even when the hardness looks good on the spec sheet. Let's get into it. One reason why I think there has been increased focus on hardness in recent years is because there has been a gradual evolution in hardness, especially in higher-end production knives and custom knives. We are seeing a growing number of knives available at 62 Rockwell C and above. It's not that high hardness knives weren't available before, but they seem to be becoming more mainstream, and it is a specification that certain knife enthusiasts are looking for when purchasing a knife. For some buyers, perhaps they are focusing too much on hardness. It can be a bit like the megapixels wars of digital cameras back in the early to mid-2000s. The number of megapixels is one measure of quality, but it can be misleading because the quality of the optics is much more important than the number of megapixels. A low-end steel or a poor heat treatment can be used to give a high Rockwell hardness number, which looks impressive on the spec sheet, but ultimately the performance of the knife may be poor. So let's start with a simple subject that is somewhat easy to understand. Edges often lose sharpness to wear. The sharp edge is abraded away, leading to a rounded apex that no longer cuts as well. A steel with higher wear resistance has better resistance to sharpness loss due to edge wear. Heat treating to higher hardness means better wear resistance. If you think about the Mohs scale of scratch hardness, talc or gypsum are easy to scratch with your fingernail. They have low wear resistance and low hardness. However, quartz, topaz, or especially diamond are very difficult to scratch and have excellent resistance to wear. Steel works similarly in that the higher its hardness, the more difficult it is to abrade away the steel. However, the differences in edge wear due to hardness are perhaps not as stark as you might think. Simple steels have relatively low wear resistance, and heat treating them to a high hardness only does so much. It has improved wear resistance at higher hardness, but a steel with a large amount of vanadium would still have vastly better wear resistance even at much lower hardness. The high vanadium steel has hard vanadium carbides that resist wear even if the steel matrix is not particularly high in hardness. The Catra test is a common test of edge wear. You can see that 60 Rockwell C CPM10V, a steel with about 10% vanadium and therefore a lot of vanadium carbide, has significantly better resistance to edge wear than 64 Rockwell C AEBL, a steel with a relatively small percentage of softer chromium carbides. So better edge wear resistance is one reason for higher hardness, but is perhaps not as important as you might think. MagnaCut has wear resistance approximately equal to steel's S35VN, CPM Crewwear, Venatus 4 Extra, and 4V. Those are all a small step down from S30V, S45VN, and M390 at equivalent hardness. MagnaCut at high hardness can match the wear resistance of a steel like S45VN at its typical hardness of 61 Rockwell C. Another common way that steels lose sharpness is through deformation. The edge will literally fold over or mushroom during use. This is of course most common with thin edges and high forces being applied. So this will depend on the type of knife, the user, and the specific thing being cut and in what way. Hardness correlates very well with strength, and strength is essentially the measure of resistance to deformation. So a steel with high hardness is more resistant to deformation. In some applications, wear does not come into play that much, and you lose sharpness primarily to other mechanisms such as deformation. So the actual strength of the material may matter more than its wear resistance. MagnaCut can be heat treated to 64 or even 65 Rockwell C when heat treated carefully along with cryogenic processing. So its upper limit for hardness is relatively high. That doesn't necessarily mean that we want to use it at that hardness, but it has that capability. As an example of an edge retention test with a mixed mode sharpness loss, I have here a test done by knife maker Sean Houston that he posted to the Spyderco forums. He used several Spyderco PM2s in different steels and measured the change in best sharpness with cuts in 3/4 inch manila rope. Each knife was sharpened to 14 degrees per side using a fixed angle sharpening system and tested at different points on the way to a total of 127 cuts. The MagnaCut PM2 here is a prototype and is not available for purchase. Sean told me that he was surprised by how much force was required to cut through the rope, especially at later stages of the test, and looking at the edges under magnification revealed deformation in the edges. The hardest knives were in CPM Crewwear at 64 Rockwell C and 52100 at 63.5 RC, and they showed the least deformation as expected. However, edge wear was also seen at the edges, most visibly apparent in the 52100 knife, as that steel has by far the lowest wear resistance in this comparison, and so still saw the worst sharpness of any knife at the end of the test. S45 VN, LMAX, and MagnaCut were similar to each other around 61.5 Rockwell, and also performed similarly on rope. However, S45 VN and LMAX have slightly better wear resistance than MagnaCut, and also lasted a bit better after 127 cuts on the rope. M390 was the most wear-resistant steel tested and was also relatively high in hardness at 62.4 RC. CPM Crewwear has somewhat less wear resistance than M390 even at this high hardness of 64 Rockwell, but because of its excellent combination of strength and wear resistance, it actually nearly matched M390, even though M390 has somewhat better wear resistance. CPM Crewwear and MagnaCut have very similar wear resistance, so we would expect 64 Rockwell MagnaCut to perform similarly. This gives us an idea of how much extra edge retention you can get in a cutting scenario that sees high forces and therefore significant amounts of deformation at the edge. However, if the edge geometry of these knives was different, or if the forces were lower or higher in the cutting test chosen, the order of the knives could change drastically. This is why sometimes I prefer to test different properties separately, such as CATRA for edge wear, hardness for strength, toughness for chipping resistance, etc., so that we can choose steels based on their strengths and weaknesses. When we do a test like rope cutting, there are a combination of factors at play, and the edge geometry we choose will also change the balance of which properties are important. This can make it difficult to figure out exactly what is going on. That doesn't make rope cutting tests bad, it just makes our analysis more challenging. I like the set of tests that Sean did because it illustrates well how hardness and wear resistance can add up together in a specific scenario. Another of the major dulling mechanisms is microchipping. When you lose sharpness to microchipping, the steel does not have sufficient toughness for the intended use. Toughness is a measure of how well a steel resists fracture. Microchipping is especially common in knives with thin edges, so steels with high toughness are preferred for applications that lose sharpness to microchipping. Fracture can be quite sudden, leading to very rapid sharpness loss, so generally we prefer edge wear to be our primary mode of dulling. Microchipping is most common when cutting hard materials and any time that chopping is involved. Which leads me to the subject of edge geometry. If your knife is seeing deformation or microchipping, you need to sharpen it with a more obtuse angle. This gives the knife better resistance to deformation and microchipping by giving it a more robust edge. In a test I did on AEBL knives, I impacted them with a steel rod at different energy levels, from a gentle tap to a loud smack. With an edge sharpened to 15 degrees per side, only 0.31 foot-pounds led to a significant chip in the edge, and 1.4 foot-pounds was so severe that the chip exceeded the size of the edge bevel, at which point the chipping is catastrophic. With an edge sharpened at 25 degrees per side, 2 foot-pounds led to only minor rippling of the edge and needed 4 foot-pounds for catastrophic chipping. So why not just sharpen everything to a very obtuse angle and make it super strong and tough? Because the more acute the angle and the thinner the edge, the better it cuts. This is a property called cutting ability, which is separate from sharpness. Sharpness is defined by how small our edge radius is, but cutting ability is controlled by the overall edge geometry. So if the sharpness is identical, the edge that is thinner and more acute will cut more easily and with less force. And this doesn't just mean that the knife will pass through what you are cutting more easily, but it also means better edge retention. In a CATRA study on 154cm and CPM 154, they varied the angle from 10 degrees per side all the way up to 28 degrees per side, or 20 to 56 degrees inclusive angle. The 10 DPS edge had more than 5 times the edge retention of 28 degrees per side. A steel with average wear resistance can outcut a so-called super steel with high wear resistance if the edge angle is dropped by only a few degrees per side. For example, let's compare CPM 154 and S90V. CPM 154 has only 60% of the wear resistance of S90V. This data point right here is S90V sharpened to 18 degrees per side. It cut about 585 mm of cardstock in the CATRA test. CPM 154 sharpened to 13.5 degrees per side outcut it at 615 mm of cardstock cut. So this trade-off in edge geometry is one of the major decisions with any knife, both by the knife manufacturer and how thin and acute to go, but also by the user, who of course has the option to sharpen his knife how he wants. go very acute and get superior cutting ability and edge retention, or go more obtuse and get better resistance to deformation and chipping. I generally recommend trying more acute and seeing how the knife does. If you start to see deformation or chipping, then back off a couple degrees until you find the sweet spot for how you use your knife. Where steel and heat treatment comes in is how well it can handle a thin, acute edge without deformation and chipping. We want high hardness for resistance to deformation and high toughness for resistance to chipping. Sometimes this combination of properties is called edge stability, or the ability of the steel to handle an acute edge without deformation or chipping. Unfortunately, having increased hardness almost always means reduced toughness. So having a steel that maintains high toughness at high hardness is desirable so that we have the best cutting performance possible. Non-stainless powder metallurgy steels generally have the best combination of hardness and toughness for a given level of wear resistance. If we look at a fixed level of wear resistance, in the past steels like CPM4V and CPM Crewwear had approximately 2 times the toughness of S35VN, even though all three have similar wear resistance. So CPM4V can be heat treated to a higher hardness for better cutting performance without being in danger of microchipping. At the higher hardness level, it also has increased edge wear resistance for overall better performance than the S35VN. Or if you are making a knife designed for hard tasks with more danger of chipping and deformation, you can leave the hardness at a lower level, such as 60 or 61 Rockwell, and take advantage of the superior toughness. The benefit to MagnaCut is that it matches the toughness and wear resistance of non-stainless steels like 4V, and therefore puts us in a new category for stainless steels. It can be heat treated to higher hardness for enhanced edge stability for more acute edges, better cutting ability, and better edge retention without sacrificing toughness when compared with previous stainless steels, or kept at a more conservative hardness when raw toughness is desired. MagnaCut toughness at 64 plus Rockwell C matches or exceeds the toughness of Vanex S35VN or Elmex when they are at only 61 Rockwell C or lower. Those were the previous gold standards for toughness with powder metallurgy stainless knife steels. For the somewhat higher edge retention steels like S30V, S45VN, and M390, MagnaCut at 64 Rockwell C has double the toughness of those steels when they are at their typical hardness of 62 Rockwell or below. So MagnaCut has the potential to handle thinner, more acute angles for superior cutting ability and edge retention. And if we compare in the 60 to 61 Rockwell C in the high toughness range, MagnaCut has significantly better toughness than other PM stainless steels such as Vanex, S35VN, XHP, and CPM 154. As a quick sidebar, another mechanism by which an edge can dull is through corrosion. I did an experiment a few years ago with knives of different levels of corrosion resistance. I dipped each knife in lemon juice and sat them in air and measured after different periods of time. The sharpness loss was significant on the carbon steel and almost non-existent with 440A stainless. So the high corrosion resistance of MagnaCut is also a benefit for this dulling mechanism. There are a couple of heat treating and processing parameters for corrosion resistance, but they don't all fit into the topic of hardness, so I won't be going into depth on those in this video. So let's get into the specifics of heat treating MagnaCut and why manufacturers and heat treaters might be picking certain hardness values over others. The place to start is the datasheet, which is hopefully where the heat treaters are starting. A feature of several Crucible datasheets is the recommended heat treatment section. For example, the S30V datasheet says to use a 1950 degree austenitize and a temper at 600 degrees for a final hardness in the range of 58 to 61 Rockwell. However, that is just one set of temperatures among many that can be chosen. The datasheet also says that you can austenitize between 1900 and 2000 degrees Fahrenheit and temper between 400 and 750 degrees. There is also an optional freezing treatment that can be performed for extra hardness. The recommended heat treatment is to provide the most general recommendation to give good performance without extremes. It shouldn't require extremely careful heat treating, meaning if the temperature is off by 10 or 20 degrees in any given direction, the steel should still be fine. The further away that you get from that recommendation, the more trouble you can get into if you don't know exactly what you are doing. For MagnaCut, the recommended heat treatment says 2050 degree austenitize and temper at 350 for a final hardness of 60 to 63 Rockwell. There is also a chart with expected hardness values for other combinations as well as what the hardness difference is if you do a cryo treatment. The datasheet says that you should expect 61.5 to 62 Rockwell C depending on whether or not you use cryo for those temperatures. I have seen somewhat higher hardness, but the datasheet is somewhat conservative in what it promises. These hardness values are for a relatively fast quench, meaning with an oil quench or what's called a plate quench. This is common with custom knife makers where they put the hot steel in between two aluminum plates and the plates draw heat out of the knife. It is faster than just cooling in air while also helping to keep the knife flat. We also did tests using vacuum furnaces at Peters Heat Treating where the steel was given an air quench under 2 bars of pressure. The steel was somewhat softer due to the slower quench speed, but with cryo the hardness was still comparable, around 61.5 Rockwell C. So depending on the specifics of the heat treatment setup, we might expect manufacturer knives to be 61 to 62 Rockwell if they follow these recommendations. Will they follow the recommendations? As with anything, it depends on how much the heat treater thinks they know better than the steel manufacturer. It can be surprising what any given person or company decides to do sometimes. If you want more hardness, there are 2 major ways of accomplishing it. One is with a higher austenitizing temperature, and one is with a lower tempering temperature, though cryogenic processing also comes into play. With a higher austenitizing temperature, more carbide is dissolved, putting more carbon in solution, and the higher the carbon in solution, the higher the hardness. However, at a certain point, the hardness begins to drop because we get what's called retained austenite. At high temperature before the steel is quenched, you convert the steel to a non-magnetic phase called austenite, and then during quenching, it transforms to a hard phase called martensite that gives us the high strength and wear resistance that we want. However, the transformation can be incomplete, leaving us with some retained austenite. When more carbon and alloy is dissolved at high temperature, this reduces the temperatures where martensite forms to a point where the transformation is incomplete at room temperature. A cold or cryo treatment can further cool the steel where more austenite transforms for more martensite and higher hardness. I have a separate video about cryo that explains how all of this works. Retained austenite in small amounts can improve toughness, but it will reduce strength and hardness, and generally we don't want it. In large amounts, it can actually reduce strength even at a given level of hardness, so we are going to take a quick detour and talk about different measures of strength. When we pull or compress a material, we can measure how it responds to stress. Under small amounts of stress, the material will lengthen or compress, and when we let go, it will bounce back to its original shape. Think of this like a rubber band. Or if you can imagine bending a paperclip, this is like bending the paperclip a small amount and letting go. However, if you apply more stress, at some point the steel will permanently deform and no longer return to its original shape. This means that you have exceeded the yield stress of the material. If you bend the steel too far, you will exceed the ultimate tensile stress of the material and it will break. Hardness correlates most strongly with ultimate tensile strength. However, it is the yield strength that determines how easily the material permanently deforms. And in some cases, we can have a material with a relatively low yield strength when compared with its ultimate tensile strength or its hardness. In this case, the steel will deform more easily than we expect based on its hardness. One of the major times this happens is when a steel has excessive retained austenite. You will see on the chart that the hardness of MagnaCut levels out above 2050 degrees and even drops when austenitizing from 2200. This is from excessive retained austenite. So even though 2200 would result in the same hardness as 2050, it would have significantly more retained austenite and be easier to deform. It would show inferior performance for its given hardness level. Another side effect is that steels with excess retained austenite show very poor sharpening behavior. I sometimes see cases where people say that such and such steel is very difficult to sharpen, but what they are actually seeing is a poor heat treatment. In a big Catra study I did, I was able to relatively easily sharpen a wide range of steels, but one in Rex 121 that had high retained austenite in it never seemed to come up sharp. I would get a burr, and then once the burr came off, it would leave a ragged edge that wasn't particularly sharp. We later did a follow-up study with a different heat treatment of Rex 121 and had no problems getting it sharp. So sometimes people blame difficulty in sharpening on a steel being very wear resistant, when in fact it is the heat treatment that is to blame. Many heat treatment shops have cryogenic processing or at least some kind of freezing treatment available, but the type of process they can do varies. They might have a freezer that goes down to negative 80 degrees Fahrenheit, or they might have a liquid nitrogen freezer that goes all the way to negative 300 degrees. They may have a freezer that cools down the steel very slowly to the target temperature, or a freezer that sits at the low temperature and the steel cools down rapidly. Some shops will do a temper on the steel before doing the cold treatment. Some shops will move the steel directly after the quench to the cold treatment, while others, because of various logistical issues, may leave the steel at room temperature for some period of time, maybe hours, before moving it to the freezer. All of these differences can matter. When steel sits at room temperature, or especially when it is tempered first, some of the retained austenite is stabilized and will not transform during a cryo treatment. So part of the reason why 2050 degrees is the recommended heat treatment for MagnaCut is because even if they are doing a temper before cryo or letting the steel sit for a long period of time, it won't have excessive retained austenite. To get the steel to its maximum levels of hardness, it would require a heat treating company or knife maker that knows how important it is to go straight to the cold treatment after quenching to get the maximum benefit. However, part of the reason they do tempering before cryo is because it reduces the risk of warping or cracking of the knives. In my opinion, it is more important to get the maximum performance benefit of the cryo treatment, but the knife companies or heat treating companies may not share that view when they have thousands of knives they need to produce. To get 64 Rockwell C MagnaCut, and this is true of most stainless knife steels that can achieve that hardness, it requires an increased austenitizing temperature in combination with a cryo treatment that occurs directly after quenching to room temperature. Another method for having increased hardness is to use a lower tempering temperature. You can temper at 300 degrees or even 275 or 250 degrees Fahrenheit and have increased hardness. There are a couple potential issues with this approach, however. One is that the blade, and especially the edge, can overheat when it is ground and sharpened. The lower the temperature of tempering, the easier it is to overheat and over-temper the edge, which would then reduce hardness. If the steel is heated above the tempering temperature, it is effectively tempered at that higher temperature, reducing hardness. Another concern is that even though the hardness is higher with these very low tempering temperatures, often the yield strength goes up as the tempering temperature increases in the low temperature range. So the steel may deform more easily than you think based on the hardness value. I usually don't recommend tempering any lower than 300 degrees Fahrenheit. Some knives have coatings applied to them that require the knife to be heated to 500 degrees or even hotter, which would mean the knife would effectively be tempered at that temperature. So sometimes knife companies use what is called the secondary hardening range of tempering. When you temper above about 750 degrees, the hardness starts to increase again with certain high alloy steels and stainless steels. So MagnaCut could be tempered in the range of 950 to 1000 degrees. This would limit the hardness to around 62, maybe 63 Rockwell C. Once the steel has been tempered at 1000 degrees, you can reheat the steel up to nearly that temperature without affecting its properties. The bigger issue is that corrosion resistance is significantly reduced when tempering in this range. Small chromium carbides are precipitated in the steel when tempered that high, which pulls chromium out of solution and reduces corrosion resistance. In my testing, this can turn even very corrosion-resistant steels like Manex or LC200N into very average steels. And for several steels I have tested like CPM 10V and CPM Crewwear, there is also a reduction in toughness when tempering at 1000 degrees instead of 400. So in general, I do not recommend tempering in that range, but it is a relatively common practice, either because of coatings or because they want more resistance to overheating in grinding and sharpening. In my testing, I saw little or no toughness difference between tempering at 350 or 400 degrees, while 350 gives you somewhat more hardness. This is why 350 is my general recommendation. However, you can go down to as low as 300 degrees when more hardness is desired. Whether this is enough temperature for grinding, sharpening, or coatings is up to the knife maker or manufacturer. Speaking of grinding and machining, this is another factor that knife manufacturers consider when choosing a hardness. Just as higher hardness means better wear resistance for edge retention, it also means it is more difficult to grind and machine the steel. This means more belts for custom knife makers, more grinding wheels for grinding machines, and milling can be very sensitive to changes in hardness. This means shorter tool life, a higher chance for the knife overheating during machining, and other issues. If the knife overheats, that is bad for final performance, of course, but can also mean more movement and warping in machining for potentially even bigger problems. Costs in tooling, belts, and grinding wheels can easily be more than the cost of the steel itself, so this is one of the major reasons that a knife maker might dial back hardness to save themselves time, money, and headaches. Another reason sometimes given by knife companies and knife manufacturers to keep the hardness in check is to facilitate ease in sharpening. Part of sharpening is material removal, which is affected by wear resistance and therefore the hardness. Some users say they don't want hardness to go beyond a certain point in case they are in a situation where all they have is a smooth river rock or the bottom of a coffee cup to sharpen on. I don't sharpen on rocks or cups, so I cannot comment much on that. But I will say that the amount of material that is removed in sharpening is relatively small, except in cases where the edge is reprofiled, meaning you are sharpening to a new edge angle. Much of the time in sharpening ends up being burr removal, cleaning up the edge, and getting a sharp apex rather than purely grinding away material. This is especially true when using very hard abrasives such as CBN or diamond. In my large Catra study, I sharpened everything from 1095 to 15V, and the material removal part of it really wasn't that big of a percentage of the sharpening process in that case. On the flip side, harder steels, assuming they have low retained austenite, often are easier to get to high levels of sharpness. In experiments by Dr. John Verhoeven in a somewhat extreme example of 40 Rockwell C versus 60 Rockwell C, the edges were rough with poor sharpness with the 40 Rockwell C knives, while the 60 Rockwell C knives had good edges. So when it comes to pure material removal, the lower wear resistance that comes from lower hardness is beneficial, but when it comes to getting the final edge, higher hardness can be beneficial. However, the perception that low hardness steel is easier to sharpen is often a provided reason for a chosen hardness, and this is unlikely to go away. Up until this point, we have primarily focused on the pros and cons and difficulties in heat treating for higher hardness. What about reduced hardness for enhanced toughness? Heat treating for lower hardness is the reverse of heat treating for higher hardness. We can either use a lower austenitizing temperature or an increased tempering temperature. In toughness testing of MagnaCut, I found that toughness was reduced when austenitizing below 2000 degrees, and the toughness was roughly equal between 2000 and 2050 degrees. This means that austenitizing below about 2050 leads to a reduced hardness-toughness balance. This is somewhat counterintuitive, as generally reduced hardness leads to improved toughness, but I have seen similar behavior in some other steels including S35VN, S30V, and S45VN. During the austenitize, you dissolve some amount of carbide. Those carbides are beneficial to wear resistance and detrimental to toughness. In general, the increased hardness washes out any effect of decreasing carbide by going higher in temperature. But in the case of these steels, there is a crossover point where going lower in temperature means more carbide and therefore lower toughness. On the subject of tempering, there is a phenomenon called tempered martensite embrittlement, where when you temper within a certain range, the toughness is reduced even though the hardness also went down. This typically happens in the range of 500 to 700 degrees Fahrenheit, though the exact temperature where it starts varies by steel. With S35VN, I found that tempering at 500 degrees led to a reduction in toughness versus a 400 degree temper. The toughness didn't fall off a cliff, the steel isn't ruined, but if you have reduced both the hardness and the toughness, then we have made the steel worse. We could have both higher hardness and toughness, which is what we want. I haven't tested the toughness of MagnaCut after tempering any higher than 400, but the fact that toughness was very similar between 350 and 400 degree tempering tells me that toughness is likely to go down with a 500 degree temper, similar to many other steels. For that reason, plus the lower limit to the austenitizing temperature, I have not seen a good way to heat treat MagnaCut to hardness levels below 60 Rockwell, so if it were up to me, I would set that as the general lower limit for hardness when seeking optimal performance. There might be some caveats, such as if the steel were being heat treated with a relatively slow quench and without a cryo treatment and tempered at 400 degrees, perhaps it might drop into the 58 to 59 Rockwell C range without negative effects. It wouldn't be 100% optimal, but I wouldn't call it improperly heat treated. There is also an emotional side to this. Knife companies and knife makers may have produced many knives in the past at a given hardness such as 60 Rockwell, and they are concerned that if they go too high that the toughness will be compromised. If the edge retention is 10 or 20% lower than it could be, that is acceptable as long as they aren't getting knives returned with broken tips or significant chipping. Some of these knife companies have very generous warranties where they are actually replacing knives for free if this type of damage occurs. And a knife company's greatest fear is that an influential knife reviewer breaks a tip off during a review. That can be damaging to the knife company's reputation. I see this emotional side coming up when knife makers contact me after getting higher than expected hardness after following one of my heat treatment recommendations. Laren, I followed your heat treatment recommendation for such and such steel and tempered at 400 degrees, but it came out at 63 Rockwell, and I think that is too high for this knife, so I'm going to bump it up to 500 and bring the hardness down. I try to talk them out of it and tell them about tempered martensite embrittlement and how both the hardness and toughness will be reduced. Some of them listen to me, but some of them actually won't. They can't get over the hurdle that 63 Rockwell sounds too high, and they will feel better if it is a couple points lower. It is hard to break old habits.
So in conclusion, one thing I think should be said is there is no need for a witch hunt looking for knives with a hardness you think is a poor choice.
A MagnaCut knife heat-treated to 61 Rockwell C is not garbage or a disgrace to the steel or whatever people are trying to say about what the ideal hardness is. If the steel is heat-treated properly, then the selected hardness is primarily opinion. Do you want enhanced strength and wear resistance, or do you want enhanced toughness? A knife maker or knife company has not used the steel incorrectly just because you had something in mind for your own preferences as a buyer. There have been many knives heat-treated to 60 RC or even lower that had excellent performance, and the fact that MagnaCut offers new performance possibilities doesn't change that. Hopefully this video answered some questions about why knife makers and manufacturers are picking one hardness versus another without simply saying it's complicated. Unfortunately, that means that we did get into some things that can be complicated, and without previous knowledge about heat treating and knife steels, you might be a little lost. I have other videos on this channel about heat treating. My website, knifesteelnerds.com, has countless articles on specific elements of heat treating, and my book, Knife Engineering, might be the easiest way to learn about steel and heat treating because it explains everything from start to finish, including more information on topics like edge geometry and properties of different steels that we could only scratch the surface of in a video like this. So if you learned something, please give a like and subscribe. Thanks to my Patreon supporters who are helping to get videos like this one made. We got several new supporters since the last video, including Chris Hancock, Chad Morris, Edward Voss, Liam Gogley, Eric Turner, Nathan Raptis, Nick Dunham, Will Red 5 Forge, Dimitri Kiatkin, Edward Edmonds, Azanelli, Matthew Reagan, Nate, Dan Barrett, Malachi Chow Green, Nat Spawnee, Mackenzie Kelsey, Jant Supply, Adam Webb, Brian Bailey, Blade HQ, and Mark Demshock. Thanks for watching.